All right, this video goes over lesson 3, the strength of a linear fit. Sometimes the association between two variables is well modeled using a linear function, but it is rare that a linear function will perfectly fit the data being modeled. Life is not perfect. So how well the line fits the data is called its strength of fit. It can be judged based on how close the data lies to the line of best fit. And again, the data is all those little dots, those data points. The closer the data lies to the line of best fit, the stronger the fit. So when all the dots are really close to almost being on that line perfectly, it's really strong. When the data points are all really far away from the data, then it's weaker. So let's rank the strength of each line as strong, moderate, weak, or none. Okay, so I'm going to actually start with B. B is an example where they're really strong. All those points are close together. And then let's see. D would be an example where they're moderate. You can definitely see the direction of the trend, but they're a little more spread out. Okay, and then A, that has a trend going upward, but that is very weak. They're pretty spread out. They are generally going upward that we can tell, but it's very weak. They're pretty spread out. And then this C would be an example of no relationship. Those dots are all over the place. Regan decided to do her science fair project on the association between the length of a person's foot and how well they do on a 50-question math quiz. She measures the length of the right foot of 100 subjects or people in centimeters and then has them take the quiz. The results are shown below. What would the linear model predict for the number of questions answered correctly if a person has a right foot that is 25 centimeters in length? Okay, so let's look at this graph. We have the length of your right foot in centimeters, and then we have the number of questions that you got correct. And these dots represent all the different people that were surveyed. So what would the linear model predict for the number of questions answered correctly if a person has a right foot that is 25 centimeters in length? So let's see, 25 centimeters in length would be right here. So if we keep going, it looks like it's I'm going to use a ruler actually. Looks like it's hitting our line of best fit right about here. Let's just make sure. It's going to be like over here. How many questions right would that be? Looks like it's just above 30. So let's see, this would be 32, 34, 36, 38. So this would be about 32. So it looks like about 32. We could figure it out exactly by using y equals 0.45x plus 20, our equation of a line for the line of best fit. 25 centimeters, that's going to be our x length. So if we plug that in, we should get our y, which is our number of questions correct, equaling about 32. Let's see what we get. So 0.45 times 25 plus 20, 31.25, which rounds to about 31 questions. Makes sense. We got 32 from the graph. The more accurate prediction would be 31. How would you rank the fit of this model? Circle one. Okay, so let's see. The dots, they're pretty spread out. It's definitely not strong. They are headed in that upward direction, but I would say this is pretty weak. Could say moderate, but I'd say that's pretty weak. All right. If Julia used her model to predict the number of questions a person would get correct on the quiz based on the right foot length, how reliable would her prediction be? Doesn't look like she's going to be too reliable. It looks like there's some sort of small relationship that the bigger your foot, the more questions you get right are, but the data points are pretty spread out. I mean, if you look carefully, like this person's foot was only 10 centimeters and they got 40 questions right, and then this person's was 35 centimeters and they also got about 40 right. So it's really not that reliable. Her prediction would not be too reliable. because there is a weak correlation / relationship between foot size and number of questions correct. Economists are trying to predict how the price per gallon of gasoline is affected by the price per barrel of oil. They created a scatter plot from the last 20 years along the line of best fit for the data. Okay, so the price of oil is listed on the x-axis, the price of gasoline on the y-axis, and here's our equation. In July of 2008, oil prices spiked to a high of $145 per barrel. What does the linear model predict the price per gallon of gasoline to be? Okay, so when it's $145 per barrel, okay. That is not on here, right? So that's going to be off to the side here. If we kept going, at least we can estimate it. This would be like 120, right? We're counting by 20s. 140, so 145 would probably be somewhere over here. So you can estimate it's going to be all the way up here above 3.5. But it's going to be better or more accurate to use our equation. Y equals 0.03x plus 0.24. Let's plug in 145 for x, because that's our x-axis, the oil. And see what we get for the price of gasoline. So 0.03 times 145 plus 0.024. 4.374. Dollars per gallon. Does that make sense? If we were to continue our trend line, it would cross about here, which, is above 3.5. That makes sense. Okay. How would you rank the fit of this model? Strong, moderate, or weak? These points are all pretty close together to that line. They're pretty close to that line, so I'd say this is definitely a strong relationship. And based on the fit of the model, how well do you think the model will predict the price of gasoline based on the price of oil? I think it would predict it well. This trend seems to be pretty accurate. All those points are close to the line of best fit, so therefore it is a good representation. So we could say the model predicts the price of gasoline based on the price of oil well. Because there is a strong correlation / relationship between the two variables. The data points are close to the line of best fit. We'll just say trend line. It's shorter. Alrighty. For each scatter plot, circle whether it shows a positive or negative correlation and whether the line of fit is strong, moderate, or weak. There will be one of each combination. Okay, so first let's do positive or negative. The slope of our line of best fit is going upward, so that would be positive. This one is headed downward, so that would be negative, upward, positive. Weak, strong, or moderate. So there's going to be one of each. So let's figure out which one's strong first. These dots are all really close together, so I would say strong. These are pretty close together, but not as great as the other ones, so we'd say moderate, and this would be our weak correlation, where there is an upward trend, but they're pretty spread out. Okay, now let's look here. We have another strong one in the first one, and that's negative. This is weak, and it's negative. And this one is moderate, and it is positive. Okay. Hot problem. What would be the strongest positive linear relationship look like on a scatter plot? Okay, so if we had our line of best fit positive, it's going to be going upward. And let's use a different color. If it is strong, the strongest possible, those dots are actually going to be right on the line. Right? If strong means they're really close to the line, strongest would be on the line. All the data points are perfectly on the line of best fit. And the same goes for this one. Strongest negative, we're going to be having a downward trend line. And all the data points will be right on the line. A phone company wanted to explore the association between age and the weekly amount of time that a person uses their phone. I would think teenagers are the most. They surveyed 200 people with the data shown in the scatter plot below, along with the line of best fit and its equation. So we have the equation given to us. Interpret the slope for the model in the context of the situation. So our slope is negative 17. Slope is change in y over change in x. So we have negative 17. Let's make it a fraction over 1. So our y is negative 17. That would be your time spent in minutes over 1 year. Negative 17. So that means that your use of the phone is decreasing by 17 minutes for every year older that you get. Okay. For every year, we'll say you increase. For every year in age you increase, the number of minutes predicted spent on the phone decreases by 17 minutes. Okay. Using the equation of the line of best fit, predict how many minutes a 13-year-old spends on their phone each week. So our equation is y equals negative 17x plus 1,550. Okay, so that means that 13-year-old age is x, right? X is age. So we're going to plug in 13 for x. Negative 17 times 13 plus 1,550 equals 1329 minutes. Right, if you look at our graph, the y-axis is minutes. Let's get it from the graph as well. So if you go to a 13-year-old, let's see, this would be 12. So 13 would be right here. And you look at your trend line, that's going to be in between 1,000 and 1,500. So yeah, that makes sense, about 1,329. Okay, strong, moderate, or weak correlation. These dots are very spread out. There is a negative trend that you can see. They are headed downward overall, but it's not very accurate. So we're going to label this as weak. How confident would you be in the predictions of the line of best fit would make about phone use based on age? I'm not very confident in this. The dots are kind of all over the place. You've got like a 20-year-old using their phone the same amount as a 70-year-old here if you look at closely at those dots. So yeah, it's safe to say that as you get older, the time spent on your phone decreases a bit overall, but it's not very accurate. I am not confident in using the line of best fit to predict phone use based on age because there is a weak correlation / relationship. Let's see, what else could we add? There is an overall downward trend. But many inconsistent data points. All right, there you go.